All right, so I want to talk about this usaco question in which that looks like a very okay. So it's really formatted on iPad, I guess. But I want to talk about this usaco question called searching for soulmates, and the reason I want to talk about this is because I thought the way that I solved it was very clean, and in fact, the solution left, I guess, that clean implementation as a bonus. And I thought that this solution was extremely overly complicated, and there's a much more intuitive way that I solved it, which helped me a lot. So I also saw other videos too, and none of them really, I guess, had the same sort of method of thinking as I did. So we all think differently, no surprise there. And so I guess I wanted to share my sort of perspective on this problem and how I solved it, and as I really like sort of the way that I reduced this question to be a really, really easy question after thinking about it in a different way. And this is my implementation. If you're wondering, it is very simple. It is just basically just recursion. It's basic recursion. I would say this question is more tricky rather than difficult, especially if you can do it in like 3 lines for the actual solve function. But it's definitely not too easy to think about why this is the way it is. But it is I'm definitely really proud of this implementation, and this runs in the fastest possible time, and it's also very short too. So just a really nice solution overall. And they did like a different solution than I did, but they're all effectively the same thing, I'm pretty sure. They all effectively get to the same place and they all work, so they're all pretty good. So basically, we're going to reduce this question, and we're going to simplify it. We're going to simplify questions. Anytime you have like a question, try to like simplify it, right? So I guess the first thing you should do is, again, we're going to explain what this number is. They basically give you a number A, number B. Your goal is to get from A to B, and you can only multiply by 2, add 1, or divide by 2. And it's easy to make some observations, like you shouldn't times 2 and then divide by 2. Those are some easy observations to make, but you want to make your observations in sort of like a methodical manner. So to do that, we look at a sample test case and look at like a non-trivial one, like 20 operations seems pretty non-trivial. So we'll look at this, and you'll notice something that's very intuitive that I think doesn't really need a rigorous proof, as they sort of proved in the solution. If we're trying to make A equal to B, then we're trying to obviously make A equal B, right? And so one can say to minimize the number of operations, it's also equivalent to always greedily reducing the distance from A to B. So again, this is very, very important because this basically solves the problem, and this is sort of motivates my solution, is that making A equal to B is effectively the same thing as always greedily reducing the distance from A to B. You realize that these are basically saying the same thing. If you want to make A equal to B in the minimum number of operations, then we're basically saying reduce the distance from A to B as fast as you can. And so always try to ask many variations of what you're trying to find, because some variations are much easier to think about. If you think about the variation I said, you don't really need to prove this. Is like this is just definition, right? Making A equal to B in minimum operations is the same thing as effectively reducing the distance as fast as you can. So this suggests that I shouldn't just since I'm trying to decrease the distance between 997 to 120. This suggests that I shouldn't multiply this number by 2, and you know that this means I should divide this number by 2. The only way I do this is adding 1 and then dividing. And so in this way, you can sort of just quickly reduce the distance between these as much as you can, and then you realize that, okay, well, this option we're given no choice but to add 1 and then divide this, right? Because obviously 125 to 120, you need to decrease this number. You can I guess only divide in this case, and and you can't subtract here. And so what gets a little bit non-obvious in this solution, I mean, I think not multiplying is pretty obvious in the beginning. Like, you're trying to reduce the distance between A and B, and it just is very non-intuitive to do that. But I think what gets this tricky is that what happens when sort of A goes underneath B. A goes underneath B. We sort of don't have an intuitive way to handle it. Like we knew that it was easy to handle A over B because, well, we only have one way to really decrease the number, or one way to really decrease the distance, and that is dividing, right? So, but what happens when it goes underneath it, right? Then we need to, then there's two ways to decrease the distance. You can either, add one, or and then like add another one, or add 66, or you could just add one and then divide, or you could like multiply, right? The question is that there's multiple ways to now decrease the distances. We can add one or multiply it by two. So this seems like a lot of a trickier. This seems like really tricky, I guess. So a better way that I thought of it was, can we just swap the numbers? Because we know how to deal. It seems like we have a really nice intuition for dealing with A greater than B. So can we just keep A always greater than B? Like without loss of generality, can we just assume A is greater than B at all times? Basically swapping the numbers once A goes underneath B. And yes, we can do this because you know that if you swap the numbers, you can just say you have the same question, but now you have to go from 120 to 63. But now you basically can subtract. You can't add. So it's effectively the same thing as swapping the numbers and saying A is greater than B. But now you can only, I guess, subtract, because when you go from the other way, well, right? Let's say I go from like I get 119. Then I go to 118, and then like I divide by 2, that's like, I don't know, 54. No, that's not 54, 59. This is the same thing as multiplying by 2, then adding 1, and then adding 1, right? So if you can swap the numbers, but then you know that you very obviously can only subtract now. So now you have the same question. We can only subtract now, but now we want to sort of decrease the distance between A and B. And there's many ways to do this again, though. You can subtract, and you can also divide. But intuitively, like I said, we always greedily try to decrease the distance from A to B as much as possible. And now we're assuming, without loss of generality, assume this case, and we'll just swap the numbers and sort of swap the operation anytime one number goes underneath another one. So if these numbers swap again, then we know we can only add instead of subtract. But again, we'll use the same sort of way of thinking, right? Making these numbers equal is effectively the same thing as like reducing the distance between them. So I want to greedily do this. So I'm going to divide this number underneath it. And then I'll swap the numbers. And then I'll sort of say, okay, now we can only add. And then you sort of see that, okay, we can only add, and now the number is greater, and so then I can do the same sort of thing again here. And so the intuition might just be like, then you might just be thinking about, okay, we just have a solution now. Is that the solution? We basically know that anytime a number goes underneath, anytime A goes underneath B, we swap it, we keep A always greater than B at all times. And then we notice that since we're trying to decrease the distance between these two numbers as much as we can, we greedily choose to divide the numbers as we can get the distance between A and B really close. This is not exactly quite true. There's one really small detail about this, and it's actually not too really difficult to think about. Let's say this is A. We assume A is always greater than B at all times. Maybe to decrease the distance, one might say we should divide by 2. Let's say dividing by 2 takes us here, right? Then this is optimal, right? We're decreasing the distance as much as we can. Now, what's interesting here is, let's say dividing by 2 takes us over here, A over 4. Now, we don't know if dividing by 2 is better than just walking directly to B by just subtracting it A over 2 minus B plus 1 times or something, or just subtracting A over 2 by 1 until you get to B. So we don't know if dividing, we don't know, like, if we divide 2 and it takes us on the other side of B, we don't know if that more optimally or more greedily decreases the distance than just directly walking to B. So in this case, we know that we actually it might be useful to do subtraction operations if dividing takes you on the other side of B. If dividing doesn't take you on the other side of B, then clearly subtracting is slower. right? But if it does, then we don't know, is it is it going to be better if we just directly walk to B rather than just dividing it and going on the other side? So this is the intuition that one sort of can have, and it feels now recursive. You sort of notice that, okay, in general, let's say we're in a state in which we can only divide and subtract. And notice how we've effectively just forgotten about multiplication because we've thought about this in a very symmetrical way, and we've simplified the problem into just division and addition and subtraction, and we just removed multiplication. So then this is very intuitive. Okay, so notice that we've reduced the question. Sorry, I had to talk to parents to not ruin the video. But notice how we so this doesn't get really pause screen recording, which is garbage. But yeah, so I guess the idea now is we have a general solution. We basically notice that we can just sort of divide the larger number by 2 as pretty much all the time, unless dividing it by 2 makes the number less than B. So if the numbers were about to swap, I guess if the numbers were about to swap, then you have to check if directly walking there is better than dividing the number by 2 in that instance. And this will make more sense when I show you the code. So it's a very nice recursive code. So basically, what we're doing is we're saying, okay, so let's define solve AB and add state. Add state is saying can we add? Because remember, if we swap the numbers, then we have the state switches. We can only subtract now. And so if the numbers are the same, we know that it takes 0 operations. And if we are adding the numbers, well then, the A mod modulus 2 is just in case we need to make the number even so we can divide it, by the way. So those are more nuances that you can sort of think about yourself. But the general idea is that if we're adding the numbers, then we will always just divide the bigger number by 2. And we know that we want to also always keep the bigger number in front. So we always assume that A is greater than B, and so that's how we sort of deal with that, max and then min. And then A plus 1 over 2 is basically saying that it's the state, right? Because if it's less than B, then we know that it's going to swap. The numbers will swap if this statement over here is not true. The numbers will swap if this statement over here is true. So that basically represents, if the numbers will swap. And so if add state, that means, and then else, basically, we know that if we're in a subtraction state, then the idea here is, in general, we can do the same thing. We can just divide the larger number, right? But if A over 2 is greater than B, like if we go back to here, if A over 2 is greater than B, then yes, it's optimal. This will decrease the distance very quickly, but if we divide this number and A over 2, for this thing about solving it on here, if you divide this number and A over 2, which is A over 4 now, A over 2 is A over 4 is A over 2, A of 2 is A of 2, if you think about it, right? But if we divide this number and it sort of takes us on the other side of B, we're not really sure. It might just be better to directly walk there. We don't know how much it is, right? So it might just be better to directly walk there. So, and that's saying we can either finish the solution by just saying directly walk there, or we can just solve the solution for this pair, where now B becomes A and B over 2 becomes B. And so that's pretty much the solution, and then we'll just I guess print it out, and that's it. So again, whoops, that is weird. And okay, yeah.